Okay, so perhaps, again, if you talk to people who have taken chemistry before, they've probably talked about moles because we do those calculations all the time. And then also maybe they've said the word stoic. They probably don't say stoichiometry. Chemists are lazy. We love short forms, but it doesn't really matter. So stoichiometry is so useful because we are going to use this to predict how much product we get. You could also use this, say you have, St. John's Chemical Factory, and you want to make a certain amount of something, then you can use stoichiometry to figure out how much reactant you should use or that you need. And that matters then, so you don't waste stuff, right? Stuff like that. So um, in grade 10, when we first talk about types, then we just sort of make it like, it seems a lot more simpler than it is. Even we talked about single and double displacement. Sometimes reactions don't occur, and we just don't consider that when you're first talking about reactions. The same thing with mole ratios or how substances are related to each other. You can't just put in whatever you feel like in a reaction and expect it to behave the way you want. In both ways, if you don't put enough or if you don't put the correct ratio, nothing will happen. Or if you don't put the correct ratio, you put more than you should or more than you expect, then you can have dangerous results. Or something like combustion, the reason it's incomplete is because there's not enough oxygen, which again gives undesirable results. So stoichiometry is like the recipe for a chemical reaction. So even let's say if you use that analogy, let's say you're going to make cookies and you forget the sugar, your cookies are not going to taste the same, right? So when you follow a recipe or you follow the mole ratio, then the reaction will go as predicted, which is always best. Okay, so we are going to use balanced chemical equations. So the second video we watched yesterday, the Bozeman guy, he talked about, I think actually he used combustion as an example. He talked about the coefficients. So yes, we need the chemical equations to be balanced, and that is going to become our mole ratio, okay? So how do we use that? So the balanced chemical equation is like a recipe. So if you don't have the correct amounts, always in moles, okay? So if you get grams, you have to change it into moles of the ingredients or the reactants, then the reaction won't make the correct result or the products. Or it'll make an inappropriate amount, and maybe it's too concentrated, too dangerous, whatever, okay? So the coefficients tell us in general what is the general mole ratio that you need, and then we can adjust that using math to what you actually have in the lab. So even if a coefficient, say, is 2, but in your lab you only have 0.5 moles, then you can adjust that using ratios, which is what we're going to do today. So a very predictable pattern using a ratio which really you could apply to anything. Like if you have one of those, what's it called, weed whackers that have gas, and you have to work out before you start it, and you have to mix diesel fuel and regular gasoline. Or if you have a job, usually they'll send you chemicals, you clean the floor, you don't just throw the stock on there. It's like 1 part of this to 2 parts water or whatever. That is stoichiometry, okay? So you're adjusting the basic recipe to what you have. And we're always going to use moles. Moles, moles, moles. Okay, so there are really 2 types of questions for Stoic in a general sense. And I've divided the textbook questions, so it says mole ratios and then it says mass. Same thing with the worksheet. There are mole questions and then ones that involve mass, sort of separated. So what we'll do before lunch is we'll do the question, we'll look at an example where you already have moles, and then after lunch we'll do the one where you have to like full on change the grams and all the stuff, okay? right, so when you're going to do Stoic, your equation has to be balanced. I forget if the textbook is ruthless and makes you balance. Oh, I did both. One of the questions is balanced, and then it looks like the next two aren't on the worksheet. So just be careful of that. I know some of you hate balancing, but it's important, okay? And then this is just in case you forget, if you're given grams, change it into moles first. So you can see now that we've done that basically in every topic since moles. Empirical formula, formula of a hydrate, now this, grams, moles, okay? And then we are going to convert between mole amounts. So again, only moles, using the coefficients in the balanced equation. There are many ways to do this. I like this ratio way because it sort of follows what you would think as a math student as well. So that's probably where you first learned ratios. It doesn't matter how many reactants you have or how many products you have. If you have a balanced equation and moles, you can convert between any of them, okay? So really when you do Stoic, we're going to do two, like a fraction here and a fraction here. Similar to even like this formula, you can only have one unknown, okay? So depending on the question, whatever you're given, make sure you use that in your ratio because you can't have more than one unknown. So usually we use X because that's the most common unknown variable. Really, you can use whatever you want. So how many moles of A? So that means that we must have been given the moles of B. So just read the question carefully because really you can do a bunch of things, okay? So if we're given the moles of B, we're going to change it or convert it into the moles of A. How do we do that? We use the coefficients. So if you do it this way, we're English readers, right? So you start on the left right away. The question says, calculate the mole amount of A. Okay, that's my X. So then this is moles. This is moles. The two tops have to match. This is A, this is the coefficient of A, so these things match. So that's like a math requirement that you would have learned before. So again, try to think about things in ways that you've thought about this, okay? So let's not use A's and B's, let's do it for real. Okay, so here's the equation. 2 hydrogens plus oxygen makes 2 water molecules. Usually when you get these questions, if the question is given to you, you're probably not going to see fraction coefficients. Again, it doesn't really matter. You would just have to divide or multiply by fractions. But in this case here, that's not really, like we don't have math expectations, right? So a lot of students don't necessarily love that. But if you want to use fractions, that's totally fine. But we usually won't, like if you're given the balanced equation. So what would we say? 2 moles of hydrogen gas, where did I get the 2 from? The coefficient, is needed to react with 1 mole of oxygen gas, because the coefficient's 1, and you're going to get 2 moles of water produced. So in math class, you can write ratios and proportions. You can write it like this, like 2 to 1 to 2, right? Stuff like that. Or if you took biology, the phenotypic ratio, and right, you do all those things. But really what we're trying to say is, in a very basic sense, we need twice the amount of hydrogen to make a reaction occur, and we're going to get 2 times the amount of water produced compared to oxygen, but the same amount in moles as hydrogen, okay? So the coefficients, you'll notice when you do these ratios, that sometimes the answers will be the same. So if they have the same coefficient, then that means you need the same mole amount, and that makes sense, okay? Does water, 2 moles of water, take up the same amount of space, the mass, as 2 moles of hydrogen gas? No, and that's why we don't use grams. Moles are all based on Avogadro's number, so it's a comparable amount, okay? So always change it into moles. So the first kind of question you're going to do, like if you go in order, okay? You'll already be given moles. You don't have to do the grams first. So The 2 to 1 to 2 is the general recipe, but we need to apply it to our lab situation. And maybe you do this. Maybe you go to make chocolate chip cookies and the recipe is going to make, 24 cookies, 2 dozen cookies, but you have half the butter you need. And then you're like, okay, I'm going to adjust the whole recipe and make half the amount. And how do you do that? You write a ratio and figure it out every single time. So you might have done this and not even realize that you were doing chemistry. The chemistry of baking. That's even a thing too. Okay, so we are given, it says, if we react 0.56 moles of oxygen, how many A, moles of hydrogen would be needed to react? That's strange English. So we can use it to predict how much hydrogen we need, and then you can also use that same mole amount to predict how much water will be produced. So that's why stoichiometry is so useful. You can compare it to what you're given one thing and find information about the other reactants and the other products. Okay? Now, how much space do you guys have? We're going to do, so maybe kind of divide your little space there into two, okay? We'll do A and B. So read the question carefully. How many moles of hydrogen? Okay, right away. That's my X. That means that everything else that I go to fill in, I can't have any more unknowns, right? You can't have more than one. So now it's up to you. Do you want to write the other side with the moles that you're given, or do you want to keep going with the H2? It doesn't really matter. So once we've decided what our unknown is, so X moles of hydrogen, that means this side has to be hydrogen. What is hydrogen's coefficient? Grace. Good. Now, what you'll find is people will just they'll just write the number. They won't even write anything else. I'm going to write the whole word so that you know where it comes from later, okay? So here in this question, I already have an X, so there has to be something that I know. What do I know? Oh, I'm given this. Moles in the top, moles in the top. So we're given the moles of oxygen. What goes in the bottom? The coefficient of oxygen. I don't have any room, so I'm going to write a short form. Sorry. I know it's a 1. These are very simple coefficients, so that's nice. Sometimes questions will be like that. Sometimes the coefficients won't be so easy. And what we're going to do next year in grade 12, we're going to apply this to energy in a reaction, how fast the reaction goes. In the second unit, we're going to apply this to what happens when something dissociates. And so we're going to apply this to other things. So eventually the numbers might not be so straightforward, okay? So now you have a choice. Sometimes I use the word cross-multiply, but then I know some math teachers say that's a bad word. So there are options to solve for this. You can do cross-multiplying. You can do 0.56 divided by 1 and then multiply by 2. It's the same thing. I realize this this 1 is not going to change the number, but again, it's up to you. So if you don't like cross multiplying, you can do this. But it's the same thing. You're basically multiplying by 2. Maybe your math brain can see that. And I'm writing over my line. But you get the same answer, okay? So now B, we're going to do the moles of water, and we're going to do the same thing. So its coefficient is 2. But now on the other side of the ratio, we have 2 mole amounts. We have, oh my goodness. Sorry guys, I wrote H2O, it's not H2O. Sorry. We have 2 mole amounts. Now we have the hydrogen and we have the oxygen. Most students, for whatever reason, will go back to the question. I don't know, maybe you don't trust yourselves that you got the right answer in A, but technically you could use that one. You might even want to, once we get the answer and we talk about it a little bit, you might even want to use this one, and I'll show you why it actually, the fact that they have the same coefficient makes them the same mole amount, so it's a little bit obvious. But again, you can do the same thing every time. So now, so really technically we've decided what our X is because that's what the question says. This side of the ratio has to be the same if you're going to use the water. We're given 0.56 moles of oxygen. Its coefficient is 1. The coefficient of 1 doesn't change, right? You can change the mole amount, but the basic recipe is always the same. I'll do the same thing. I'll write it out both ways. So the black way is not cross-multiplying. The purple way is, you get the same answer, right? What you pick what you like, okay? Why is the moles of hydrogen the same as the moles of water? Because they have the same coefficients. So if you are comparing moles, then their mole amount will always be the same. If you changed it to grams, would they take up the same amount of space or have the same mass? No, okay? So that's why we like moles. When we're doing stuff like this, obviously in a practical way, if you were going to go to a lab, the scales don't measure moles. We would have to convert it. But in a theoretical way, you can use this to predict this is how much I need, we need less oxygen, or whatever. Okay, so we'll do the second example after lunch. So right now you can do the mole ratios from the textbook. You can also do like the mole to mole calculations, the first part on the worksheet. The answers on the worksheet are at the bottom. The solutions are on that board and on D2L, okay?